Hello everybody, welcome back to our channel. In this episode we're going to be solving a Physics 7B position, velocity and acceleration practice problem. As usual, if you're finding this content helpful, please make sure to leave a like and subscribe. It really helps our channel a lot. So let's go ahead and read this problem. I'm just going to read part 1 of the problem because it is sort of a long statement, but please make sure to pause the video and actually read both parts because we will be solving the entire thing. So the guys from the Dude Perfect show are about to perform their next epic trick shot. To test his strength, Tyler throws a ball of a 122.5 meters tall building. When the ball leaves Tyler's hand, it has a velocity of 9 meters per second in the horizontal direction. Assume air resistance is negligible and remember to use G is equal to 9.8 meters per second squared. Part A. How long will it take for the ball to hit the ground and what is the horizontal distance traveled? Okay, so as you can see, I have everything written down here. So I have a very basic picture of Tyler and the ball, which leaves Tyler's hand at 9 meters per second horizontally. Now, we do know that this ball is going to travel like this, and it's going to hit the ground somewhere over here. And this ball will basically travel in two directions, so it will have traveled a horizontal distance and it also traveled a vertical distance. Now the vertical distance was basically given to us. It is this 122.5 meters. However, we need to be careful because when you're talking about delta y, direction matters. Well, also for delta x for that matter. But what I'm trying to say is that even though this height is 122 meters, delta y itself, like the actual travel distance, is negative 122.5 meters. And this is very, very important because delta y being negative means that the ball went down. If you start using your equations with a positive number here, then that basically means that your ball went up. And that is not okay, but that is not what happened on this problem. So we do need to be very mindful about that. Now, something that I really like doing with these problems is, and this is something that I will always do and I just stand by it, I like to put up a little chart over here and separate all of the information that I know for the x component and for the y component. This really helps me out because I sometimes mess up by numbers. And if I don't make this very clear to myself, sometimes when I'm using an equation for the y component, I'll sneak in something from the x component, and obviously that is not good. So it's just a very visual tool. It helps me out a lot, so I'm just gonna go ahead and do it this way because I'm pretty sure that a lot of you will really like this method. So obviously we don't know the travel distance of y, we're trying to figure that out. But we do know delta y, which is negative 122.5 meters. We do know both of the accelerations because if I draw a force diagram, the only force that is affecting this ball once it leaves Tyler's hand is force by gravity, right? So a force by gravity is my net force because, well, it is my only force. Then that is equal to mass times acceleration. So that means that mg is equal to mass times acceleration. So that basically means that on acceleration for x, this is a 0. There is no air friction and there are not any forces on the x-axis. And for y, using f net is equal to ma, I can tell that this is just g. Now again, direction is going to really matter over here. Gravity is pointing downwards, so you really want to make sure that this is a negative 9.8 meters per second squared. Otherwise, when you're plugging this into your equations, the equation is going to think that gravity is pointing up, and that is, of course, just not going to give you a right answer. Now, I do know my initial velocity is because Tyler threw this exactly horizontally, which means that these 9 meters per second go here, and this is a 0. Now, I don't have my final velocity for y, but I do know that because acceleration is equal to 0 over here, that velocity is just gonna stay constant. If you're not convinced about it, just look at this equation, right? You have your initial velocity and this is 0. Well, that means that your velocity is gonna stay the same. So this is gonna be 9, like this. And this is basically all of the information that I have. Well, just from looking at this, what I want to do is I want to start with the y component over here. And let me tell you why. And this is really why I like splitting this up, because I get to look at my options and I get to, you know, decide very quickly what's gonna work. I have 3 equations with delta x over here. However, I would get stuck trying to find delta x because this is basically, I don't have delta t over here, I don't have delta t over here, and then this is just gonna give me, what is this gonna give me? Oh, this is not gonna give me delta x because a is equal to 0. So if I try using this equation, then okay, I have this and this, but this is gonna cancel out. So this is just not gonna be useful. So this is why I would get stuck using these equations. So what I can do is try to find delta t first, and then see, because I do need to find delta t anyways, and then see if that helps. So what I'm going to do is I'm going to start with my y component, which is this information and these equations, and I do need to find delta t. So let's see. I have 3 equations with delta t. However, this one I can't really use because I don't have b final, so this one I would get stuck. And this one, as you can see, we have the same situation. If I use this equation, I'm just gonna get stuck over here because I don't have b final. So really the only option for me, if I wanna go ahead and figure out delta t without doing b final first, is this equation. So I'm just gonna go ahead and use this equation. However, I just want to make it clear that you could technically use this equation first, find b final, and then use this one to find delta t. But that is an extra step, and we don't really like taking, you know, extra steps on the 7B, especially if this was a quiz. So I'm just going to use this equation. I'm just going to copy the equation. Alright, so now what we want from this is finding delta t. So I'm just gonna go ahead and substitute all of my numbers and solve for delta t. So this is negative 122.5. This is equal to 0 times delta t, which cancels out, plus 1/2 of negative 9.8 delta t squared. So this is negative 122.5 is equal to negative 9.8 divided by 2 delta t squared. Negatives go away, and delta t is equal to 122.5 times 2 divided by 9.8, take a square root. So let's just go ahead and put this on a calculator. Let's see. 122.5 times 2 divided by 9.8, and then take a square root, and this is equal to 5 seconds. So this is equal to 5 seconds, and because it took the ball 5 seconds to travel this horizontal distance, then that means that it took it 5 seconds to travel this vertical distance, I'm sorry. That means that it took it 5 seconds to travel this horizontal distance. So this is 5 seconds as well. So now that I have more information, I can go back and see if maybe that helps me figure out what delta x is, and the answer is going to be yes. I do, well, at this point, honestly, I have everything but delta x, so literally I could use whatever I want, except this one, of course, because it would cancel out. So let's just go ahead and use the same one. Let's just use the same equation, but with x. Delta x is equal to b xi delta t plus 1/2 half ax delta t squared. Let's just substitute. Delta x is equal to initial velocity is equal to 9 because I'm using the x component now. Delta t is equal to 5 seconds. And then plus 1/2, oh, this is a 0, right? Oh, this is 5 seconds squared. Well, it doesn't matter, everything is 0 over here. So delta x is just equal to 9 times 5, so that is going to be equal to 45 meters. Final answer. So this is 45 meters. And there we go. And that basically solves the first part of our problem. Just Tyler throwing a basketball from this point to this point. So let's just go ahead and read part 2, which I have over here. So part 2 of this problem says, now suppose there is a second building, a distance d away, and there is a basketball hoop. You know, this is perfect. You need a basketball hoop exactly halfway between the buildings, raised to a height of 44.1 meters. That is a very big, all right. Tyler throws the ball off the building with the same velocity as part A. The ball bounces off the second building once and then passes through the hoop. So this is, you know, it hits the building and then just passes through the hoop. This is perfect. Of course, it's gonna pass through the hoop. Assume the ball bounces off the wall instantaneously. Note that the figure below is not drawn to scale. So, question, if the wall does not affect the vertical component of the ball's velocity, how much time will it take for the ball to reach the hoop? Alright, so on part A, Tyler throws the ball and it basically follows, you know, this path right here. But now there is a building. So obviously, instead of just completing this path and traveling the 45 meters horizontally in one go, it's just gonna bounce and it's just gonna end up here. However, we do need to be very picky on the instructions and like really read the instructions, because the instructions are telling us two important things. The ball bounces off the wall instantaneously. That means that hitting this wall happened in 0 seconds at all, which means delta t, you know, the collision hitting the wall is 0. That means that delta p, in terms of magnitude at least, is equal to 0, which means that the ball is not gaining any impulse. The ball is not changing velocity, which is something that the problem then says. It says very specifically the wall is not affecting the velocity, the vertical component of the ball's velocity. So, and this is why, because it happened instantaneously, right? So basically, what I'm trying to get to here is that this entire thing, hitting the wall and then bouncing back, happened on the exact same 5 seconds as before. Because this basically didn't take any seconds. So delta t total is 5 seconds. So starting here, hitting the wall, getting here, 5 seconds. Now another thing that is very important is that my delta y is still gonna be, you know, negative 122. Well, this is total, right? Negative 122.5 meters, because I traveled the same distance. And on that sense, my delta x total is also gonna be 45 meters, unlisted magnitude, because this wall didn't change anything. The wall might, I mean, the hoop might have as well been over here, honestly. Okay, so now we have to think this through. Now, the only reason why the final answer isn't 5 seconds is because this 5 seconds is ball hitting here, getting here to the floor. And what the question is asking us is not that. What the question is asking us, what is the time for, in which it basically hits the hoop. So not the time from here, here, and here. It's the time from here, here, and then all the way over here. So that is the thing that's going to make a difference over here, right? So the answer is not 5. It has to be less than 5, obviously. So let's just go ahead and figure what that is. This is a very interesting problem. So for this part, which is part 2, my delta y is actually not the total delta y, but my delta y is gonna be, so this total distance minus the 44.1 meters, so that my traveled, or is a vertical distance, is just gonna be, you know, this delta y, right? So let's just go ahead and figure out what that number is. So this is gonna be 122.5 minus 44.1. So this is 78.4 meters, obviously, and negative because it still went down, even though it didn't went down all the way, it's still going down. Okay, so my acceleration on y is still negative 9.8. That hasn't really changed. My initial velocity is still 0 because that didn't really change. So I feel like with this we have enough information to just literally recalculate delta y in this exact same way, except now we want to figure out what is using a new delta y, we're gonna get a new delta t. So let's just go ahead and do that. So the equation that I used before and the equation that worked was delta y is equal to by initial times delta t plus 1/2 ay delta t squared. So delta y in this case is negative 78.4. This is equal to 0 because by was initially 0, just as before. And this is negative 9.8 divided by 2 times delta t squared. So delta t is going to be, negatives go away, just as before. 78.4 times 2 divided by 9.8, take a square root. So this delta t is going to be 78.4 times 2 divided by 9.8, take a square root. 4 seconds is the final answer. So in this new scenario, Tyler throws the ball, it hits here. We could actually find this, but it didn't ask us to. It takes 4 seconds for this to happen, and then an additional second to go from here to here. So that's interesting. Alright, so let's just look at the next part. If the wall changes the direction of the ball's horizontal velocity without affecting its magnitude, again, that's the thing again, how far apart are the walls? In other words, what is this distance? Okay, so this is again, you know, the thing that matters. This wall is just a means for this to change its direction. It is not adding an impulse. It is not putting an impulse on the ball. It is not putting a force on the wall, on the ball. I'm sorry. It's not really changing anything. So we can basically calculate a traveled horizontal distance. So let's see. Okay, yes, so that's what we're gonna do. We're gonna find delta x again. So let's work out our delta x. So we want a delta x, and what we have is the same initial velocity, final velocity, and we do have a new delta t. The new delta t is equal to 4 seconds. So let's just go ahead and recalculate delta x. And this is gonna be, this new delta x is not gonna be the total travel distance. It's gonna be the travel distance from this point to this point. So the total travel distance would be this distance and then this distance. But what I'm gonna do is I'm gonna calculate the travel distance from here, bounce, and then just come back halfway. And I'm gonna show you why in a second. But first, let's just get that distance. So I'm just gonna use the same equation as before. Delta X is equal to BXI times delta T plus 1/2 AX delta T squared. AX is equal to 0. So delta X in this case is just initial velocity, which is equal to 9 times time, which is equal to 4. So total travel distance is equal to 36 meters. But what does this mean? Because I just found a delta X, I didn't really found a D, this distance. But this is going to be very helpful because just think about it. So the total horizontal distance that this ball traveled was 36 meters. And in terms of horizontal distance, what was the actual traveling? Well, you went from this side of the wall to this side of the wall, you hit the wall, and then horizontally you travel halfway back, right? Remember, this is just X component, so this is just the horizontal distance that you traveled. And this is very helpful because even though I didn't straight up found D, I almost did, because in terms of D, what I did was I traveled a D distance and then halfway back. So in terms of distance, a D distance plus a half D distance is equal to 36 meters, right? It's a distance and a half of D. So if 3/2, so this is 3/2 of D is equal to 36 meters, then D is equal to 2/3 of 36, that will be 24 meters. There we go. So it traveled 24 meters to the right and then 12 meters to the left, and that is how the total travel distance ended up being 36 meters. Alright, so this basically finishes the Dude Perfect problem. So guys, if you enjoy this content, if it's helping you, we would really appreciate it if you could leave a like and just leave a comment supporting this channel. It would really mean a lot to me and to us, the Physics 7 Angels. If you have any questions, please do let me know. I do read the comments, and I will see you guys on the next video. Bye!